Hello, previously we learned phasors and impedances and how to analyze AC circuit at steady state. Today we will learn another important concept, the AC steady state power. We generate usually power as an AC waveform and also we transmit the power over long distances using AC transmission lines. Therefore, we need to learn terms such as average power, real and reactive power, complex power, power factor, RMS value, etc. In general, we are interested in the power generated and absorbed by a circuit element of an electrical circuit. The instantaneous power delivered to a circuit element, according to the passive convention, is the product of voltage and current. So in other words, P is equal to V times I. The unit of power is watts. Suppose Vt is a periodic function with a period t. Mathematically, we can write this as Vt is equal to Vt plus the period t. Then, accordingly, the current will also be a periodic function, which can be represented as It is equal to It plus the period t. And accordingly, the instantaneous power P will be also a periodic function. Here, I plotted a sinusoidal voltage of the form cosine 2 pi times 5t and similarly another sinusoidal waveform for the current It is equal to sine 2 pi times 5t. So both of them have 5 Hertz frequency and have the amplitude 1, and they don't have phase, but one of them is cosine and one of them is sine. And when I found the instantaneous power by multiplying the corresponding V and I elements, I end up here for the power with a periodic waveform as well. So basically, when I multiply the voltage and current, which are periodic waveforms, I end up with a periodic power. Let us see whether this is the case for more complicated voltage and current waveforms. Here, for the voltage, we have the summation of two different sinusoidals with different frequencies, 5 Hz and 4 Hz. And as you can see, we have a periodic waveform, but it just has a complicated shape. Similarly, for the current, we have also the summation of two periodic sinusoidals. At the end, we have a sinusoidal waveform for the current as well. And when we find the instantaneous power, we have a periodic waveform here as well. Here you see the power waveform repeating itself, even though the waveform is quite complicated and does not look like a regular sinusoidal. The average power P is given by P is equal to 1 over T, the period, times an integral of pt dt from an arbitrary point t0 till t0 plus 1 period. In electrical circuits, we usually deal with sinusoidal voltages and currents. The voltage can be given in the form of V of t is equal to Vm times cosine omega t plus theta v, and the current I of t can be given as Im times cosine omega t plus theta I, and therefore the instantaneous power can be calculated as P of t is equal to Vt times It, and this is equal to Vm times Im times cosine omega t plus theta v times cosine omega t plus theta I. Now, if we use the trigonometric identity, 2 times cosine alpha times cosine beta is equal to cosine alpha plus beta plus cosine alpha minus beta, we can write this instantaneous power equation 1 as P of t is equal to Vm times Im divided by 2 times, in parentheses, cosine theta v minus theta I plus cosine 2 omega t plus theta v plus theta I. In the previous slide, we found that the instantaneous power for a circuit element with sinusoidal voltage and current is given by this equation 2. And let us calculate the average power delivered to this element. where P is equal to 1 over T times an integral from 0 till T, this expression 2. And we can divide this expression into two integrals. One of them is 1 over T times from 0 to T, the integral of Vm times Im divided by 2 times cosine theta V minus theta I times dt. And the other one is plus 1 over T, an integral from 0 to T, Vm Im over 2 times this cosine term. Now, let's have a closer look to this cosine term. This cosine term over one period will have the integral value of 0. And therefore, this second term will drop. This goes to 0. Our integral will only consist of this part. And here what we observe is that none of the terms are related to dt, and therefore they are all constants and they can be taken out of the integral. And my integral reduces itself to a simple integral of the integral from 0 to t dt. And the result of this integral is, let's do it together, from 0 to t dt is equal to t, we can write it here as 1, t from 0 to t, and this will be equal to t. And note here I divide by t, so this t divided by t, I end up with p is equal to Vm times Im divided by 2 times cosine theta V minus theta I. This is very interesting. Basically, the average power does not depend on time. The average power does not depend on the period. It just depends on the amplitude of the voltage and the amplitude of the current, and the phase of the voltage and current are very important. For instance, if both the voltage and current have the same phase, we have cosine 0, so average power will be equal to Vm times Im divided by 2. But on the other hand, imagine that the phase difference is plus 90 or minus 90 degrees. In that case, cosine 90 or cosine minus 90 is equal to 0. In other words, even though I will have some voltage forms with some frequency and amplitude, if their phase is 90 degrees different, the average power delivered to a system will be equal to 0. So this is an interesting result. So the circuit on the right is in steady state. It is an RL circuit supplied by a sinusoidal voltage source. The mesh current is this, I of t, is 721 milliamperes times cosine 100 t minus 41 degrees. And the element voltages are given here. We need to find the average power delivered to each device in the circuit, the voltage source, the resistor, and the inductor. So in general, the average power is given by P is equal to Vm times Im divided by 2 times cosine theta V minus theta I. Now let's calculate this for each of the components. We need to find the average power delivered to each device in the circuit, but in the case of voltage supply, we realize that it does not adhere to the passive convention. The current is entering from the negative terminal. Therefore, there will be power delivered by the voltage supply or power supplied by the voltage supply, which can be found as PS is equal to this is 721 milliamperes, so I will write it as 0.721 amperes times 20 volts divided by 2 times cosine theta V. Theta V is minus 15 degrees minus theta I, which is minus 41 degrees. So accordingly, this will be equal to 7.21 watts times cosine 26 degrees, and this is equal to 6.48 watts. Basically, the power delivered by the voltage supply will be on average 6.48 watts for one period. On the other hand, resistor adheres to the passive convention because the current is entering from the positive terminal. Therefore, the power delivered to the resistor will be equal to 18 volts times 0.721 divided by 2 times cosine theta v minus 41 degrees minus 41 degrees. So this will be simply equal to 1 because we have cosine 0, and the whole expression will be equal to 6.48 watts again. So basically the resistor will absorb all the power delivered by the voltage supply on average. So I can speculate that maybe the inductor will not receive anything over one cycle because it is a energy storing element and it does not dissipate anything, but we will see. And finally, let us calculate the average power delivered to the inductor. PL will be equal to 8.66 volts times 0.721 amperes divided by 2 times cosine, again theta v is 49 degrees minus 41 degrees, and we will have here cosine 90 degrees, which is equal to 0, and therefore this whole expression becomes 0 watts. So basically the average power delivered to the inductor over one period is equal to 0 watts. The current through the resistor is shown in the figure. We need to find the average power delivered to this resistor. We call this waveform as the sawtooth waveform. And I will start by writing the current as an analytical expression for one period. So here I have 0, here I have t, here I have the value Im. So the slope here is Im divided by t, and I can write I of t is equal to Im over the period t times time t, and this will be valid for this range. Now, at the instant when I do this, I need to find the instantaneous power and then just kind of like work with the integral to find the average power. I cannot use the equation which I used in the previous slide for sinusoidal currents because this is not sinusoidal. So P is equal to I squared times R, which is equal to Im squared divided by t squared times small case t squared, and this is multiplied by r, and this is also valid for this range from 0 to period t. Now, in order to find the average power, I need to work with this integral. P is equal to 1 over t times from 0 to t. Here, this expression Im squared over t squared times r times t to the second power dt. And here I have bunch of constants. I will get them out of this equation, otherwise it will become quite confusing. It will be Im squared times r divided by t to the third power times, let me take the integral, t to the third power divided by 3, and integration bounds are t and 0. At 0, this expression will be equal to 0, and at t, this expression will be t to the third power. So it will be equal to Im squared times r divided by t to the third power times t to the third power divided by 3, and this term will cancel that term, and the average power will end up being Im squared times r divided by 3. So basically this triangular waveform has 1/3 the average power of as if we would have a constant current of Im through that circuit element. Interesting. When we connect an electrical device, such as a washing machine or laptop computer, to the wall plug in Kazakhstan, we tell that we connected to 220 volts. Indeed, this is so in most of the countries in the world, except select a few which use 110 volts instead of 220. The voltage from the wall is at 60 Hz sinusoidal with the average value 0 volts. So what is this 220 volts? 220 volts is not indeed the amplitude of the sinusoidal waveform. It is the effective value of that waveform. The effective value of a voltage is a measure of its effectiveness in delivering power to a load resistor. The goal is to find a DC V effective or I effective, such in the case of the voltage from the wall 220 volts, that will deliver the same average power to the resistor as it would be delivered by a periodical source. Let us look at this example. I have here some type of sinusoidal source delivering some amount of power to this resistor. And here I want to find a V effective, which is a constant voltage, which will deliver the same amount of power to this resistor. So that 220 volts is this V effective value. Now we will learn how to find that. The average power delivered to the resistor R shown in the previous circuit is given by equation 1. P is equal to 1 over T, integral from 0 to the period T, I squared R dt. And the power delivered by the direct current is simply P is equal to I effective squared times R. In order to find I effective, the DC current that will deliver the same power as the periodic current in equation 1, we need to equate 1 and 2, and we end up with this expression 3. And if I solve this expression for I effective, we get the square root of 1 over t times integral from 0 to period t I squared dt. The effective current is the root of the mean of the squared value. Therefore, it is called root mean square current, IRMS. We can also find the VRMS using the same methodology. Let us find the RMS value of a sinusoidally varying current. The current is given by I is equal to Im times cosine omega t. And in the previous slide, we found the effective or RMS value of the current as this expression shown here. And if I take this current and plug into this expression, I end up with the equation number 1. Here I need to take an integral, and I have a slight problem because I don't know how to take the integral of cosine square omega theta. However, I can use here the following trigonometric identity. 2 times cosine squared alpha is equal to 1 plus cosine 2 alpha, and therefore 1 will become this expression, and here I can divide that integral into 2 parts. Therefore, I have an expression here and another expression there. Here, when you look to the second expression, you realize that we are taking an integral of a sinusoidal function over a complete period. Therefore, it will become 0. And in the first case, we just have for the integral the value of t. And therefore, this whole expression will simplify itself to this square root of Im squared divided by 2t times t. And t's will cancel each other, and we will end up with Im divided by square root of 2 as the IRMS value of a sinusoidally varying current. In the case of power transmission, for the voltage 220 volt refers to this RMS or effective value, and we can calculate the amplitude of that waveform as 220 volts times square root of 2, and which is equal to 311 volts. Now we know what that Vm is. Alright, previously for this circuit we found the average power in one period, and now we will find the effective value. And in order to find the effective value, let us write the current again. IT is equal to, I found it earlier in this lecture, Im over T times T between 0 and period T. And I effective simply will be square root of 1 over T integral from 0 to T I squared dt, and this will be equal to, I effective will be equal to square root of 1 over T integral from 0 to T I m squared divided by T squared times T dt, T squared. Let's extend this a little bit. And I can take all of these terms which are constants out. So accordingly I have again the square root I effective is equal to 1 over T to the third power. Here I have Im squared integral from 0 to T squared dt, and this is equal to, again inside square root, Im squared divided by T to the third power, basically T to the third power divided by 3. I took that integral already, and accordingly if these terms cancel each other, I end up with, for I effective, Im divided by square root of 3. This is interesting because previously we found the effective value of a sinusoidal waveform, and the effective value of a sawtooth waveform with the same amplitude is less than the sinusoidal waveform. This is somewhat interesting.